Rao Bhim 8.7 Spectral Representation. This section is very important. Unfortunately, this section is a very sad victim of Rao Bhim way of presenting. So I shall take the liberty of slightly restructuring this section. We start with the theorem 8.7.5. We called it Schur decomposition in the last video. We have already seen the proof of this theorem in the last video. It says that we have to work with complex field. Then for any square matrix over complex field, you can write it in the form of P star Tp, which basically says that every square matrix over C is similar to a upper triangular matrix. To an upper triangular matrix, not only that, this change of basis matrix may be chosen to be a unitary matrix, that is, P star P is equal to identity. I have already mentioned that this theorem should be part of your thought process. So we start with this theorem. We have already proved it by direct induction. Now, in the last video, we were discussing how various matrices may be proved to be semi-simple, that is, similar to diagonal matrices. In this video, we shall grow the list by including a number of very important classes of matrices that are semi-simple. The first of them is complex Hermitian matrices, that is, matrices that satisfy this condition A star equal to A. Then real symmetric matrices where A prime, that is A transpose, is equal to A. You might think that if I just take a real symmetric matrix, that also happens to be a complex Hermitian matrix. So why do I really need something different? That is because we are going to use this theorem, and this theorem works only over C. So to make sure that the conclusion works even for real thing requires some additional work. Then we shall consider normal matrices, which are defined in definition 8.7.6. These are defined as square matrices that satisfy this condition, and we shall see that normal matrices actually have both these two things as special cases, which are also semi-simple. Not only that, in all these cases, we will have a very special form of similarity, namely where this non-singular matrix will also happen to be unitary. Such a similarity is called unitarily similar. Thus, we say that here A and T are unitarily similar. And this theorem says that over the complex field, every square matrix is unitarily similar to an upper triangular matrix T. So, when we are working with a square matrix, we might as well assume that it is an upper triangular matrix. First, we shall start with the proof of this. Every complex Hermitian matrix is unitarily similar to a diagonal matrix, that is, it is semi-simple in an unitary way, and that is the main thing of theorem 8.7.3, which the book has proved in a very complicated way. But we shall prove it in a very straightforward way simply by observing that when I am working with a square matrix, I might as well think that it is an upper triangular matrix. So, if I am given A to be upper triangular together with this condition, what do I get? So, instead of A, I am writing T, which is an upper triangular matrix similar, unitarily similar to A. So, I have T star equal to T. Then T is an upper triangular matrix like that, or everything here is 0. So T star is a lower triangular matrix with the zeros here. If they are the same, then you can easily see that this part will be 0 and this part will be 0, and whatever you have here should match. Now remember, whatever you have here is just complex conjugate of this. So this number is complex conjugate of this number. This is my T star and this is my T. So this number must also be real. So all these things must be real. So if I additionally give you that A is an upper triangular matrix, you immediately conclude that this matrix must be actually a diagonal matrix with real entries. Now, by virtue of this theorem, you are going to conclude immediately that any complex Hermitian matrix is not only semi-simple, it is unitarily semi-simple, and the diagonal matrix is also going to have real entries. So we have proved what is called the spectral representation for complex Hermitian matrices. If you start with a complex Hermitian matrix, then you have A equal to P star dP for some unitary matrix P and some real diagonal matrix D. Now this has lots of simple corollaries. Number 1, theorem 8.7.1, if you have a complex Hermitian matrix, then all the eigenvalues must be real, because we have already seen that these entries, the diagonal entries of D, are precisely the eigenvalues. And observe that this is true for all complex Hermitian matrices, so real symmetric matrices are also included in them. Now here is another corollary, which is given as theorem 8.7.2, spectral representation for real symmetric matrices. We will just try to adapt the same theorem for real symmetric cases, because we are emboldened by the fact that even for complex case we are anyway getting real diagonal entries. So here I will be working with real symmetric, which means A prime equal to A. Then I should be able to write the same thing, but I want to make it stronger. I want to say no, not unitary, but you can actually work with something even stronger, namely orthogonal. Remember, an orthogonal matrix is also unitary. It's an unitary matrix with all real entries, so we can actually write this. Now this may not be equal, it may not be immediately obvious why we can actually have this matrix also a real matrix, because we know that complex numbers sometimes multiply to produce real numbers. So how do I know that we can choose P to be a real matrix? This actually follows from the simple observation that if I take any real square matrix and any real eigenvalue, then I can choose a real eigenvector. And why is that? The reason is very simple. Suppose this is a real matrix, square matrix, and this is some eigenvalue, real or not. In that case, naturally, we can get some BV equal to lambda V. Now I am given the additional information that lambda happens to be a real number. Then all that you do is, in general, you know that this is something which is in complex vector space Cn. You just look at its real part and imaginary part separately. Since B is real and lambda is real, so they will influence both the parts equally well, and you can choose A, B to be just the real part or just the imaginary part, whichever is non-zero. So here is the proof that I have written down. Since it is an eigenvalue, so there is some non-null vector which satisfies this. In general, this is a complex vector. You look at the real part and the imaginary part. At least one of them must be non-zero, because W is non-zero. So just use that here and you will get the result. So once you have that, you come back here and you will say that instead of working with just any eigenvectors, I will pick my eigenvectors in that way and then I will get this result. So I can actually choose my matrices, my unitary matrices to be real ones, so they will be orthogonal matrices, and this is spectral representation for real symmetric matrices. Now theorem 8.7.4 is a Rao Bhim version of spectral representation of complex Hermitian. There is no new content in it, just making minor variation and writing it out in a very bloated way. So I have a star equal to A, then I already know that I can write it as P star times a diagonal matrix times P. Now what they are doing is they can of course permute these things up and down by just permuting the rows and columns of these two matrices, so that if there are any zero entries, they will bring it down here. So you'll have zeros up to some point and all the non-zero things up there. And that's what they have said, that without loss of generality, I can assume these things to be a diagonal matrix with real non-zero entries, well, all these things are 0, and in that case you can easily see that the rank of this matrix will be R, and these being non-singular matrices, they will not change the rank, so R will be equal to rank of A. And then they have expanded this, writing it in terms of vector multiplication, and thus produce lots of equivalent forms, which are things that you should not waste time remembering. Now, the way we proved spectral representation of complex Hermitian matrices was just to think about an upper triangular matrix T. So, we saw that if I put the condition of complex Hermitian on an upper triangular matrix, that forces it to be a diagonal matrix. Now, naturally, the question now becomes, can we put some weaker condition on upper triangular matrices, which will also force it to be a diagonal matrix? And a little bit of playing around will easily convince you that this is precisely the condition that you need, namely the matrix should be normal. A normal matrix is one which satisfies this condition, A star A equal to A star. Now, the claim is, if a triangular matrix, an upper triangular matrix, satisfies this normality condition, then it must be actually a diagonal matrix. Thus, we have this fact: if we start with an upper triangular matrix, or lower triangular matrix for that matter, then if it is normal, then it is diagonal. If it is diagonal, then it is normal. If it is diagonal, then trivially it is normal, because then A star is same as A bar, and so you are getting basically A bar on both sides, so they are just the same. The non-trivial part is, if it is normal, then it is diagonal. That is almost trivial to prove, but once you have this fact, you immediately get theorem 8.7.8, which says, over complex field you start with a square matrix, then it is unitarily similar to a diagonal matrix if and only if A is a normal matrix. Now, the proof is very straightforward, because I will first say that I am working with a square matrix over C, so without loss of generality, I will assume that A is actually an upper triangular matrix, and then this reduces to this, because once you have an upper triangular matrix, you can just show that it is diagonal, so you can take P to be just the identity matrix. So the thing reduces to proving this fact of 8.7.7. Now, this direction is trivial. To prove that direction, just notice how the various entries are laid out. So I have an upper triangular matrix. So this is my T, this is my T star, and this is my T star, and this is my T. And I am equating the ijth entry here with the ijth entry here. So you can see that these zeros meet with those things, and many of the things will be lost. So when you are multiplying this with this, you will basically get certain norm squares, because everything kind of meets its complex conjugate when I take, say, I equal to j. And when you are doing it, you are getting something very similar. Again, 0 meets 0, and you will get something. And from that, things will just immediately cancel out, and you will see that all the off diagonals must be equal to 0. I am not going into the details, because once you write it down, you will get it immediately. It is very trivial. And once you have that, you get this immediately. Theorem 8.7.9 is again a Rao Bhim bloated version of just theorem 8.7.8, so contains no additional information. Then the chapter continues with certain results on unitary matrices, most of which we have already discussed when we were discussing orthogonal matrices and inner products and things like that. There is just one thing which is extra and useful. It says that unitary matrices have eigenvalue modulus equal to 1. For orthogonal matrices, this is very natural, because we know orthogonal matrices represent either reflection or rotation, and reflection and rotation cannot really change the length of anything. The same proof works here also. Suppose A is a unitary matrix and you have this, then what I can say is that if I am multiplying V, what can I say about the norm of AV and norm of V? We know that they must be the same, because it is unitary. And what does that force me to have? This forces me to have mod lambda equal to 1. That's it. So that is basically the end of this section, which was one of the most important sections in the entire book.